Okay, so first question is, what if we calculate how fast something was traveling? Could we calculate the distance? Sure, yeah. We could probably figure out time as well, right? How do we calculate distance? I'll give you a hint. You guys did stuff like this in science. Yeah. Rate times time is distance. We did a bunch of these little RTD boxes, right? We went rate times time equals distance. Okay? Ben, how fast are you running in this makeup problem?
20 miles an hour.
20 miles an hour, you're fast. So Ben's running at 20 miles an hour. What's your time? How long did you run 20 miles an hour? How many hours?
3.
3 hours. That's incredible. Shauna, how far did you run? 60 miles. That's pretty spectacular. Congratulations, you just shattered the marathon record. Kate, you're running too. How fast do you run, Kate?
25 miles.
25 miles an hour. Do we know how long you ran? We don't know. So what should we call it if we don't know? Yeah, let's call it. Okay. John, what's her distance? 25 minutes. And let's have a little fun with this. Jamie, let's say Kate ran 30 miles further than Ben. Can we figure out how long Kate ran for? Oh. How? So who? Sure. So if I went 25 Kate plus 30, that would equal Ben? Is that right? Not quite. We don't want to add 30 to Kate's because Kate's 30 further. What should we do to Kate's distance to make it equal to Ben's distance? Yeah, we want to subtract it, right? We want to take 30 away from Kate. Instead of taking 30 away, where could we add 30? Or we could add 30 to Ben, right? Either way, we get the same equation. So subtracting 30 from this side is the same as adding 30 to that side. And this is just a matter of solving. So you get 25K equals 90. You do a little division, you get, what is that, 3 and 15 25ths, 3 and 3/5 hours, which is also, I think, say again?
3.6.
3 and 6/10, 6/10 simplifies to 3/5.
Yeah.
So Kate, you are also now the new world record holder for the marathon. Sorry, Ben, it was short-lived, but congratulations to both. Okay, so what if we want to calculate how fast something falls? Could we do that? Let's talk a little bit about things that you have learned in science class. How fast does something fall? 9.8. Does anybody know what that is in feet? Because we're going to deal with feet. It is going to be 32 feet per second squared. Okay? What we're going to do is use the formula for calculating distance of a falling object, which is 1/2 the acceleration of gravity times time squared. What should I just plug in for acceleration of gravity? What did we just say it was? Yeah, so really what we're going to do is we're going to use the equation 16 t squared. Okay? And that is going to be distance of a falling object. And so to do that, what we're going to do is we're going to use my lovely little daughter's play ball as an assistant in this. And we're going to go up to the commons with a stopwatch. And we're going to calculate how high our staircase is. All right? So what we have to do here is calculate the distance from the top railing to the ground. And what we're going to do is we're going to use a ball and a stopwatch. Okay? So what we're going to need to do is hold it perfectly in line with the top of the rail. And when you drop it, I'll start the time. When it hits, I'll end the time. We're going to do this a few times. And then we're going to take the average of our times just to get the best guess. Because there is human error in this, especially since it is not a super long drop. Don't hit anybody, Caroline. Okay, are you ready?
Yes.
When you drop it, I will start it. Okay, so first one is 0.72. Let's get that recorded. So 0.72 is the first one, right? Someone else drop it?
What? No, you don't. Yeah, I'll be
Okay, oops, did not stop it at the right time. You gotta give me some warning, Caroline.
sorry.
No, who's your chance? Someone else? Now.
Then you want to take it. Alright. Drop.
Okay, 0.81. Let's do 2 more. Okay. Okay, 0.90. 1 more to get an average. Come on. Where's your go-go guys on? Okay, last one. Ready and okay, 0.84. All right, so real quick, that'll probably, how about we call that 0.85? Anybody any issues with that? All right, so as we come down real quick, we're gonna have a quick conversation about a couple other things. We're gonna do some calculating. Movie Inside, did you guys see the movie Inside Out? It was so cute. It was so sad. Like, I was watching, I'm like, this is the most depressing little kids movie I've ever seen. All right, so obviously there's one factor working on the ball right here, right? What is the one factor? Gravity. Okay. Is there any way I could put another factor into this? What else could I possibly do? The weight, yeah. So you'd think like, if we were to take 2 different things, like, which one's going to fall faster? Okay, what if I do this? About the same speed, right? So the weight doesn't actually, it's like that trick question, what falls faster, a ton of feathers or a ton of bricks? It falls the same speed as a fractal. What else can I do to this to change the falling of this? You could push it down, that sort of starts your initial velocity, right? So you could throw it, which is initial velocity. What if you threw it up? You could throw it up, you could throw it down, you can throw it any which way. So that's going to add a little bit to our equation as well. So what we're going to do is we're going to go back, we're going to look at just dropping, but we're going to think about what you could do with what we call initial velocity. All right? So we're going to head back to the classroom, do a little bit of calculating. So first things we're going to do is we're going to calculate how far the ball has fallen. We're going to use this 16t squared as our distance. So we got 16t squared equals our distance. What was our t value we're going to use? Yeah, 8,500. So let's plug in 8,500. Let's square that to get our distance. 85 squared on a calculator is
7,225.
okay, and let's multiply that by 16. 11 and 5,600 feet. So before we do anything else, I always like to think reasonable or unreasonable that the top of the railing is 1.5 feet taller than a basketball hoop. Reasonable or unreasonable? Yeah, that seems fairly reasonable. Of course, what is some of the big reasons why that might not be perfectly accurate? The timing, right? The timing can be extremely flawed, right? Well, that's fairly reasonable, so we probably did a pretty good job, right? So let's talk about what we could do with this graph. So let's take this 16t squared and let's think about how we can apply it to a quadratic equation. So let's pull out our graphing calculators. I'm going to pull up our little Desmos, and we're going to look at what this looks like on a graph. So go to your y equals screen and type in 16 x squared, because x is our variable. In this case,
we type in?
16x squared. What do you think a reasonable window is going to be on this? Nicholas, give me a reasonable window for everybody to look at.
I guess X max 500.
Ooh, way smaller. Way smaller. Way smaller. Let's go single digits. How about we go 5 and -5? And then we go for Y max min. Let's go 0 to, I don't know, 100. Okay? So you should end up with something that looks a little bit like this, right? Okay? So what we have is a nice little parabola. What did we say the height was at 8500ths?
Wait, what is the X max and min?
So I went -3 to 3 for the X min, X max, and then for the Y min, Y max, I went 0 to 100. You might want to put like -1 to see it cross at the origin. And the reason is, what does the Y stand for here? What are we talking about when dropping something? So yeah, the height that we're dropping it from. So what you can do is a couple different things. You can go on your trace feature, but let's go to 8500ths for our X value. Is 8500ths about 11?
Yeah.
Yeah, it's like right there, right? Why does it keep going? There it is. So yeah, right there, about 11. So we did a pretty good job with that. What if the time was, I don't know, 5 times longer? Okay, so we're looking at like 4 seconds. Okay, what's the height going to be if it falls for 4 seconds? About how many feet? Yeah, about 256, right? Why is that? Because we are squaring it, so it's going up at a much higher rate. You know, it's not linear, things like that. So what do you think would happen? Okay, so here's a good question. Let's think, we're dealing with quadratics here, right? What do you think would happen if we threw it up? We threw it up. Let's talk about what that equation would look like. What would that look like if we threw something into the air? Think quadratic equations.
Well, would you need like some measurement of the force that you use?
Yeah, you need to know what your initial velocity would be, right? So what do our normal quadratic equations look like? What do we normally see? Give me like an example of a normal one. Go ahead.
0 equals x squared plus 10x
Perfect.
5.
Okay? So let's think about throwing something into the air. Think about throwing something into the air. What does the 5 represent?
The intercept?
The intercept, the y-intercept, yeah. So if we're talking about throwing something into the air, the 5 is the y-intercept. What does the 5 represent? Not exactly how far you threw it up.
Or where it started from?
Where you started, yeah, that's where you started. Okay, and so I'm going to throw a 16 here just because that's how far things fall. What do you think the 10 represents then? What's the only other factor in this case? Ben sort of mentioned it already. Initial velocity. Yeah, this is the speed which we throw. So we call that V sub t, initial velocity, which is not what you'll ever, you might see it on one of your packets, but so that's our initial velocity. When we have class again, which is not going to be Friday, it's going to be Monday, we'll throw things up. Okay? We'll know time, we'll know where we started from, but we'll be able to calculate how fast someone threw something, which I think is pretty cool. Don't you think that's cool?
Oh, wait, so if you don't have the 10x, that means you didn't throw it up?
No, so if this whole term was gone,
Yeah.
you wouldn't have it. No. So what you're saying is, what is the distance if you drop something from 5 feet?
Yeah.
Okay, yeah. So having this middle term or the v value is assuming that you threw it up.
Yeah.
Okay, great question. All right, so what we're going to do in the last few minutes of class is we're going to get you some work to get started on. You guys will continue working on this Thursday. And you guys have a fun homework assignment to work on as well. I think it's fun. It's difference of squares. I love difference of squares.